Great. So for that demonstration, what I'll be doing, like mentioned, is I'll go through a typical workflow from CAD to simulation, and then do a design change and see if the meshes and if the boundary conditions are applied, and also look a little bit more at what's possible in NX from a simulation perspective. So I'll go through these different steps. So I'll start with the CAD capabilities. I'll look at the meshing tools, the simulation capabilities, post-processing. So sometimes you don't want an expert user of NX or SimCenter to be able to review your results. So is it possible to export the results to neutral format like JT so that someone can just freely open the model, look at the results, and that's it? So that's possible. In terms of scalable solutions, I think throughout the first part of the journey, we've talked about automation. This is all the kind of things we can do in NX. Automate workflows or processes, and one of them is reverse engineering. So that could be done as well. So we'll see a typical problem we've found in the turbine industry where we want to get the cold geometry out of hot simulation. So we'll see how this can be done, and then we'll finish by doing non-negligible geometry change, like changing the curvature of a blade, for instance, which is typically not an easy feat to do, especially to keep that CAD associativity. So that's what I'll show. All right. So this is kind of a segment of a compressor, right? So we have a main disk and we have a few blades that are assembled. Here I'm at the CAD level and I'm working with assembly. So although I'm referring to 45 identical blade components, under the hood it's the same part that you can modify and replicate. So that's typical of other tools. Now what's kind of different here is that the CAD is embedded. So unlike tools like ANSYS SpaceClaim or SolidWorks, working either at the assembly level or at the part level in this case, all of our CAD capabilities are available. So I could go here, look at one of my blades, and I could look at the history tree and see all of the different features that were used to create that geometry. I could add some of them, so I could create a command where I pull up the face, and you'll see it will modify the face or increase the thickness of it for all of the different components at the same time. So you can work, as we call that, in context of the assembly. Same thing, I could go back to my disk here, right? And let's say I'd like to resize my face. So that's kind of a hole. I note that's currently 188 millimeters. I could decide, hey, I want this smaller. Can resize the face, and the operation is saved in the part navigator. Okay, so in terms of CAD capabilities, there's everything you need to be creative, and then you're back at your main assembly. Now, a typical challenge, and that's mostly in the case of analysts working in different groups and designers, is to have kind of a well thought out pipeline between the two, right? If a designer makes a modification, you would obviously want the model to update for analysts. But if an analyst makes changes for XY reasons, mostly for simplifying the heaviness of the model, you don't want that modifications to reflect on the designer's part, because it's not a real modification. It's just physical assumptions for structural analysis, for instance. So we have what we call the concept of idealized part, or idealization. Okay, so that's essentially a one-way highway between the designer and the analyst. Okay, so let me show you how it works. So what we could do, let's say this is the final model from a design perspective, but if I'm a structural analysis, hey, there's kind of a symmetry in that model, right? So can I leverage that without modifying the whole model, right? Well, I can. So we have this tool called Wave, and I'll show you what this does in just a moment, which allows me to pick only a few selected components that I want to use in my structural simulation. Okay. Actually, let me just do solid body. Oops. Okay. I hide all of this. Oops. Right. And now what I can do is I could split that geometry. And by splitting that geometry, I'm not modifying the designer's part. I'm modifying an idealized instance of that part, which is here. if you look at my tree. So that is the master part that the designer has been working on. And this is what we call an idealized version of it that's physically tied to the master part. So all the features are tied from the master CAD are tied to that idealized version, allowing a pipeline, a one-way highway for that information to flow. Okay, so let's say I'm the analyst. I want to work on this. I only want part of it because I'm going to use symmetry. So let's do this here. So let's split that disk. Whoops. Apologies. A single face. Sorry, let me just do this again. There we go. Right, so I'm going to split that body again in two, take this guy, use this as a reference. I'm going to keep this, and let's say from a structural standpoint, as a structural analyst, I only want to work on this guy, right? But then if you save your model and the analyst decides to make a change, right, you don't want it to modify the geometry, and that's your original geometry here. So if someone, if the analyst decides to change again that dimension of the disk, so we can always go there, make the work part, resize the face, change this to 150. Let's make it drastic, 100 millimeters. Okay, so that's a change done by the designer. But then if I'm the analyst, I'm the structural analyst, and I'm going to go back to my model, I'll see that this has been extended, so that's much further. Okay, so changes to the analyst model does not affect the designer's model, but changes from the designer's model affect the CA model. That's kind of the idea, and that works also in the context of a PLM environment. Okay, so that whole structure is embedded in Teamcenter, which is our PLM platform. Okay, with a different versioning, because an idealized part, the designer's part could have multiple versions or revisions of the CA model, and the CA model can also have multiple revisions of the CAD model. So that's tied right in. Okay, so technically our part is ready for meshing. So what we'll do is we'll go directly in our meshing environment by creating a new FEM. In this case, we'll want to use a multi-physics environment, and that the only difference is that it exposes different elements, right? Elements compatible for both analysis. In this case, it's cyclic symmetry, so we can all do this or not, right? So it's up to us to determine what kind of analysis we want. And here, we can mesh. So at the meshing level, or at the mesh level, we have our one-click tools to generate quick, efficient mesh. So let's say you want to do a preliminary analysis, just click tetrahedral, right? Pick a mesh, automatically determine the size, click apply, and a mesh will be created on the fly. And that mesh is associative to the geometry again. Can do the same thing for the top part, click apply, and that's it. Okay, so that's the simplest way of creating mesh in NX. So there's multiple kinds of elements. But if you want to be a bit more granular, and let's say you're doing some refinement, of course, all of the different tools and mesh controls are available to refine meshes in different areas of the model. And what's also nice is that these refinement tools can be tied to what we call selection recipes. So the same quantities I've used for topology optimization, right? So you can select or create meshes that point to features. Mesh all my parts of a certain color, or mesh all my parts with specific names in it. So if we go back here, take solid body and do properties, right? So we can define a new attribute called mesh size 5 millimeter, for instance. Okay, and all of this can be automated, by the way. I'm just taking the long way here. So all of your bodies can have different parameters or attributes, right? Either embedded into a standard workflow. Whoops. Give me a second. Clear content. Let me do another one here, which is called mesh, and the value is going to be. My bad. Do it again. New attribute. Mesh.
I can imagine this could get quite complicated though, because typically it's not just creating a different size tetrahedral mesh. You know, you need mesh controls and different things. So
Yep, like mesh controls for holes, for instance.
yeah.
Right. So this can also be automated using selection recipe without even having to define the hole. So let me just create here. So not sure why it didn't show up, but it doesn't matter. So I'll go back here, and in my selection recipe, I can point to a user attribute. In this case, the user attribute would be a string. So the name was, I believe, mesh size. And every part that has a string mesh size as an attribute set to 5 millimeters can be meshed by pointing to that recipe. Okay. Same thing for mesh controls. Let's say you do have a part with multiple holes, and typically around holes what you'll want to do is something like this, so a mapped hole. So you'll want a certain number of layers of elements around that hole to make sure that your bolted connection is you don't have any discontinuities. But these guys can also point to selection recipes. They're like this. So the mapped hole by default will automatically look for all circular features. So what you can do is simply create a selection recipe, polygon body, name. Simply that's called star. That's a little trick. That's called a wildcard. So all bodies, take everything in your model. Create it, mesh control, mapped hole, selection recipe, this guy. So this will automatically refine your mesh around all the holes in your model, all the holes it can find based on whatever you input. Okay. And these kind of strategies really, I think it depends on your creativity. We have point selection recipes, but we also have stack. So it can be very specific. Take all the parts of a certain color, or take all the parts, look at a particular face with a certain curvature around a particular point, mesh, mesh in a particular specific size. So it can really go deep in terms of stack, right? So we can have as many stacks as we want.
Can selection recipes be transferred from one part to another, or is it a case of templates?
So that's a great question. So these selection recipes can be used both at the FEM and at the simulation level. So now I'm showcasing for elements, but it can be used for boundary conditions. But those are saved as template. Okay, so when we created our, let's say, let me just go back to the part here real quick. When I create a new FEM, these guys, like Nastran, are essentially templates. But I could have a template called, Rolls-Royce template, or a blank template that you customized up front, and that already includes all the different selection recipes, all the different meshes that you've created that point to those recipes, so that when you open it with a particular CAD, everything gets meshed on the fly.
Quality, could you put in specific quality checks, relevant quality checks?
Yes, yep. So if I go here,
As part of that template.
actually when defining the mesh that points to that selection recipe, we have some advanced options here that I'm just going to expand. So in terms of the mesh quality, right? You can specify a certain tolerance, Jacobians, depending on where you want to put the nodes. All of these here can be adjusted beforehand before creating that.
Yeah, but I guess what I'm saying is, because what Volvo would accept as an acceptable show mesh is not necessarily what Ford would or JLR. They've all got their own little flavours of what's a pass fail. So
Okay.
could you have a template for a JLR mesh, a Volvo mesh, a Ford mesh?
As long as those criteria can be translated into let's say minimum mesh size, or
That's exactly what. Yeah.
then yes.
Quad angles and
Quad angles, yeah.
percentage of triangles and all that kind of stuff.
Yeah, minimum Jacobian or maximum Jacobian, yeah. As long as those can be translated into functional requirements, we can have them in there. Okay. Material library, I think I've already covered it. So in this case, I'm not going to go through it again. But let's say my mesh is okay, very rough, but let's say it's okay. Of course, there's a lot of different checks we can do, right? We can look at the material directions. We can look at the total mass, number of elements, especially when you want to look at scalable solutions. You want to look at how many degrees of freedom you have in your model, right? So this you can analyze directly from there. Then we can go at the simulation level and run the multiphysics solutions, for instance. So in this multiphysics solutions, that one's particularly useful because it combines structural boundary conditions and also thermal boundary conditions. And all of the boundary conditions are kind of vertical intent. So there's always a meaning behind those. It's not just fixed this and that degrees of freedom, but it's more explicit. In that case, what I could do a simple surface-to-surface gluing. Let's say I want to glue the elements from the blade to the disc. So what I'll do is I'll just hide the mesh and use our automatic detection tools to find all the faces that are physically touching each other within a certain tolerance. So we don't need to specify the faces for that glue connection. Right? So we can just directly create it, and you'll see all the faces have been detected. Okay. Now what you'll want, of course, is to have those, associative to the model. So that's one way of creating connections. Another way of making sure our parts are connected is by connecting the mesh instead of connecting them at the simulation level. Okay, so from a structural standpoint, it's different, right? If you merge the elements on top of each other, or if you create what we call glue connections between elements, you won't get the same results. Depends on what's for what. So in terms of automatic creation, all right, thank you. All right. In terms of the automatic connections, we can use something similar, where in this case the mesh will be tied to each other. Okay, and then everything is saved on the navigator tree here on the left-hand side, so it's very easy to track what you've done. If you share a model with another colleague, it's very easy to track what's been accomplished in that particular model. Okay, I've heard mission cycles or condition sequences earlier, I think from you. We do have those kinds of features. So in terms of substeps, we can define multiple cases. We can define a case for nonlinear static that varies from 0 to 100 seconds, then apply a thermal load. In this case, here, if I look at the different steps, I can create static, I can do a dynamic loads within the same environment, one after the other. I can run in normal modes, get the natural frequencies, load it mechanically and thermally, and then recalculate the frequencies to see what changed from hot to cold. Right? Do I have a different behavior? So all of this you can accomplish. But especially when you have transient mission cycles, that can be very complicated. Sometimes creating those steps and time-dependent boundary conditions can be challenging. So what we have is something called condition sequences, which is essentially mission cycles or duty cycles, where you import a set of conditions. Okay. You can either import it or create it and save it as a template. And these conditions are saved as parameters, value versus time. Okay. So for instance, if I look at this one now and I plot it, you'll see that. So throughout my simulation, this particular parameter, NH, which is, I'll show the expression menu soon, will vary along the simulation over this profile. And you can edit those profiles directly. This one, if I take it for example, is constant throughout my simulation. And my sequence is this. Okay, so from 0 to 2,000 seconds. Right, so that's pretty useful instead of having to specifically or manually define those time-varying boundary conditions every single time. You can save them as a condition sequence log if you wish.
Yeah, something I've been looking at. So, for example, I'm looking at a heat exchanger that's got PCMs in it, so it charges and discharges. So at the moment, I'm running it in like a transient cycle for 3 hours at a certain load.
Mm-hmm.
But I'd like to set a condition to say when it reaches the phase change point and it's equal, then stop and discharge, and then discharge until so I get a simulation, and the outputs would be basically the time to charge and time to discharge, and then I want to run analysis on that. Would using the sequence manager be the right tool in that application?
I think you could use it, but I think there's maybe an approach that might be better. Okay. So right now, in a solver, there's the option of stopping the analysis whenever you reach a particular thermal condition. So let's say you reach that condition where your phase change starts or ends. You can stop the analysis and save the results. And then from there, you can rerun an analysis like kind of very easily actually by using those results as a baseline. Right. But I think the key here that's in the platform right now is a stopping condition based on a particular criteria.
Yeah.
And there's also a nice feature in the flow solver, once you've reached steady state on the flow side, although you may not have reached steady state on the thermal side, you can freeze the flow field. So get to an accelerated transient response, coupled response. So that's something that it's called freeze flow.
Yeah.
And you can direct you to that.
We use that actually because we run profiles that can last up to 200 hours. So we started freezing the flow field, but then the time step had to be adjusted for that as well. It got
Absolutely, yeah.
Right.
a little bit complicated, but yeah, we figured that out. Probably need a bit of time with you to figure out some of these things that I'm working on.
Yeah. Well, actually, this is something we can follow up directly on it, like show you how to accomplish that
Yeah,
particular
yeah.
stopping condition right afterwards.
Just pick one of Jacques' cards afterwards. And hey, just a quick time check.
Yes.
You have 8 minutes left, my friend.
Oh,
So if we
geez.
want to leave these good people.
That's
I
true.
think
That's right.
you know,
Okay.
go way before the traffic there. I'm
So-
learning
so
that
what I'll-
traffic is an issue. So.
What I'll do is I do have a few slides afterwards for co-simulation and Amundsen. That's pretty, kind of nice. So what I'll do is, if you guys could provide a card, I can send you the slides and the content I was planning to show on those immediately afterwards. So just before I forget, if you have a card, I'm not sure whose I've taken already. Yeah. Okay. So yeah, I'll be sending the material. Do you have yours? Excellent. All right. Okay. So in terms of contingent sequence, that's pretty much it. There's devils in the details of course. So I'd be happy to do follow-up sessions. In terms of results, okay. All of the post-processing tools are available in NX. But I think one of the most time-consuming and painful step is to post-process the results, like making them look sharp and neat, and in a report format. So we do have tools now that can expedite that process. One of them is the report generator, but also layout states, which allows you to apply specific dispositions of the views, specific results, specific legends or markers automatically, right? So that you can save them as template and reuse them, and it will read whatever results is loaded. So it's not result specific, and just apply the proper kind of orientation and then banded profile. Okay, so that's kind of new, and that's very useful for comparing what if scenarios. So you can have multiple models open with multiple results and apply this one on each, so that you have identical views side by side with different results. Okay, so that's a new feature called layout states. Personally, from a post-processing tool, that's my favorite, right? So you can play with layouts. So in this case, I'm only showing, one besides the other. So for the results, but I could have as many as I would like. So look at this other window here, and apply the layout state somewhere else. Okay, those are saved as templates. All right. How about design change? Okay, so this is something we've been building up to. So we do have our simulation model with all the different boundary conditions that are tied to the geometry. We have the elements that are tied to geometry. Now, what if I want to, kind of slightly modify the curvature of this blade? Will this, what will I need to recreate? Do I need to reinvent the wheel? Right. So let's do kind of this change here. So we'll actually go all the way to the CAD, where the view that a designer would potentially have, and let's try changing the curvature of this face, right, which is not typically easy, especially in that case, since the blade was imported from a third-party software. You do not necessarily, or you don't always have the history tree. So can you directly play with the topology and change that? And we can using our advanced surfacing tool here. So you can go here, right? Then you see there's a few grid points that are spread out through my face, so it recognizes the different edges, the different points. So I can take that geometry here, let's see, and just push that edge a little bit. Okay, so it changes the curvature. You see the original one. I'll pull it a little bit more, let's say from here. Okay, so let's apply that change. Right, so the geometry change, you see in the history tree, that feature has been saved. So you can always edit it, cancel it, modify it. Okay. Then we'll just go back to the FEM, which is our mesher. You'll get a notice that something's changed. Maybe have a look at your geometry, see if it needs to be updated. Okay. So I'm not sure if you can see it. You'll see the current mesh, and you'll see the new mesh that needs to create. Right? So that's new edge. So that's what we can do. We can update it here. Okay, so then the mesh has been automatically updated. Right? If you had connections, those also would regenerate. If I had mesh mating, this would also be regenerated. And the elements uses the same material properties as the previous one. And if I go back to my boundary conditions, which also were quite complicated, you'll see that they're still all tied to my geometry. So all you have to do is rerun the analysis and use layout states to compare the results side by side by looking at this, by using our template. So really the whole process is associative. Both if you do the modifications in the in NX itself, or if you decide to import a new geometry. Let me just do this here. From a geometry that comes from, in the software. Maybe the modifications of the blade or the assembly was done in SolidWorks. You could also re-import the SolidWorks part in it. So the modification need not be happening in the software itself. Okay. So maybe just to close a little bit, as I've mentioned, we've talked a lot about automation and scalable environment. One of the things that can be done is kind of automation in NX. So automation for your particular businesses or for your particular applications. In this case here, what we've done is automation for the turbine industry, where we do hot to cold analysis. So our original geometry, right, might look like this when it's built, but once you apply the loads, thermal loads, rotation, right, structural loads, it might distort to be in that position here. Okay, so now can we reverse engineering and design in order that once loaded, the geometry comes back to the original brown one, right? It's kind of cheating a little bit, right? Reversing. So if you were to do this manually, how would you do it? Change the design, apply the load, see if it goes back, and then calculate the distances. It's not straightforward. It's really iterative and challenging. But with our solution, we, for instance, can automate that process for you with a one-click button. So it's a bit small now. Let's see if I can, well, I'll let it play a little bit before. But you see this is the geometry. So the geometry once loaded, and you see that its profile is exactly what you would want in operation. But now the resulting, the initial geometry that you need in order to get there is this one. Okay. So using automation tool, we can really quickly, simplify or automate complex workflows such as this one, which realistically, if you wanted to do this manually, it's unthinkable, or you're in for a long run.